Hello, dear students. Welcome back to my YouTube channel. I hope I'm audible and visible to all of you. So today we will be discussing lecture number 4 on magnetic effect of current. Up to lecture number 4, we concluded Biot-Savart Law and the application part due to the finite wire, infinite wire, axial position of the ring, or the arc one, right? Then we had a discussion based on the different numericals. So this in this particular lecture we will be starting about Ampere's law, Ampere's circuitous law. Okay, so let's start now. I guess my screen is visible to you now. First, I need to check it by my own side. 1 second. Okay, now. Okay, so we are dealing with lecture number 4. Lecture number 4. Yes, it is visible. So now let's start Ampere's circuitous law. Circuitous law. Okay. So first of all, I will write the statement of this law, then we will have the discussion on it. Okay. So if we write the statement, it states that the line integral of magnetic field over a closed loop over a closed loop is equal to product of permeability of free space and summation of current enclosed by 1 second. Okay, beta, hi, hello. Enclosed by closed loop. Okay, I guess in electrostatic we had the law as a Coulomb's law. So Coulomb's law deal with the forces between charges. Then we had one more type, that is the electric intensity or electric field intensity. Done. But as we discussed about electric field intensity deals with the smaller dimensional objects. And if we want to find out the electric field intensity, for that thing we can use the Gauss's law. In the same way here, if we want to find the magnitude of magnetic field, we are having two laws, Biot-Savart law and Ampere's circuitous law. Working of the both laws same. Both laws are applicable, or we can use this law to find out magnetic field at a point. Then in Gauss's law, we were dealing with the imaginary sort of area. Done. Imaginary integration of A dot dA. summation of q by epsilon naught. There we were using a Gauss's surface, imaginary surface. So this law is a replica of the Gauss's surface or Gauss's law. Look now, if we now want to write the whole thing into a mathematical equations, I can write line integral. It is a closed. This is closed integration of your magnetic field with the dl length. This is line integration is equals to nu naught times. This is permeability, and this particular sign represents a summation of enclosed current. This is enclosed current. Hello, beta. Look now. This particular thing represents summation. Summation means add. Then now look now. If we are having wires, one infinite wire, one more infinite wire, here one more infinite wire, here one more infinite wire. Okay, infinite means coming from infinite goes towards infinite. A very long wire, a very long wire. In this wire, current I1 is flowing. This wire, current I2 is flowing. This wire, current I3 is flowing. This wire, current I4 is flowing. Okay. Now, let us suppose we want to calculate magnetic field across these two. So I will make a loop. This means imaginary loop. Dotted lines means this imaginary loop. It simply indicates I want to calculate the effect of current I1 and I2. Sorry, it is I1 and I2. Look now. What is I enclosed? Enclosed means we need to take only that current which is inside the loop. I guess if I need to write summation of I guess it is only I1 plus I2. Why, sir? Here this symbol, because direction of current is same. That is why we are at I1 plus I2. I1 plus I2. Then this is all about Ampere's circuit law. We are not going into the depth because we had a very good discussion in the Gauss's law. So you can write B dot dl equals to nu naught summation of I enclosed. Now, if this thing is clear to you now, let us write application, a first application part of it. I will write magnetic field due to long straight current carrying wire. First application. And you know that we had discussed this particular part with the Biot-Savart Law also. And my answer was nu naught I 2 pi r. Look now, in this law we can also define it. So if we are having an infinite long wire with current I is flowing through it in this direction. Now we will take any point here. So at this particular point P, I need to calculate the magnetic field. What I need to do, I will make a loop. This is my loop. You can see now if current I is going upside, so here it is cross. This one is dot. Okay, so it will go in this way. Look, in this way. Now I will take a small element, DL element. This one is R. So this would be my DL. This could be my DL. Done. So you can see DL and B. This is B inside and DL. Direction is same. So can I write now theta is 0 degree? What is theta? Angle between B and DL. Now use this law. Integration of B dot DL equals to nu naught summation of current I. B dot, I will write B DL cos theta. Nu naught, internal current is only I. Look, I will closer integration of B DL cos 0 degree nu naught I. So cos 0 is 1. So I will write closer integration of B DL nu naught I. I will take B outside. It is constant. So I will write DL nu naught I. B. So what will be the length of this particular ring? It is in the shape of a circle. So DL means it is circumference. So I guess it is circumference is only 2 pi r. Nu naught I. Can I write now? B came out to be, it is nu naught I divided by 2 pi r. This is my final expression. I guess this expression is same as that we discussed in our by using Biot-Savart law. Okay. Done. Done, beta. Easy. Okay. Second now. So if I just tell you, look, one thing that you need to take care of it, that not applicable, I can write not applicable. This law is not applicable for finite length wire. Finite length. Reason is same that we discussed it in Gauss's law. Also, Gauss's law is not applicable for finite length wires. Okay, why? Because these are not highly symmetry, not symmetrical. These are not symmetrical, not symmetrical. So we cannot use Biot-Savart law here. Okay, so sorry, Ampere circular law. If you want to apply the Ampere circular law, it should be a symmetrical body or symmetrical distribution of current. Okay, now second application part. Now second application part. Okay, right here, second application part. Second application part is hollow cylinder. Hollow cylinder or hollow cylinder second name is hollow pipe. Hollow pipe. One more name is thin walled pipe. If you find any one name in your paper, so the meaning is same. Hollow cylinder, hollow pipe, thin walled pipe. Names are same, meaning same. Okay. Hollow means which doesn't contain anything inside. No. So I will make firstly hollow. Look. It won't be like this. Yes. What happens to it? 1 second. Nothing, no worries. Okay, so this one is my pipe. Is my pipe. A hollow cylinder. Hollow means nothing is inside. Nothing is inside. Okay, just like a glass, nothing is inside. Only a very thin walled pipe is there. If current is flowing I, if we are giving current I, okay, so where the current will flow? I guess if you are giving current I, if you are giving current I to it, this current will flow only on surface. Only on surface. Why? Because current need is a body, no? Charge need is a sphere, a surface where it will travel. So if inside no nothing is there, so charge won't travel, right? So charge will be only on the surface. So current will be only on the surface. So now, if we will take a point here, point A, suppose. I guess point A is outside, so I will write first point. First point outside. Outside. Now, if you want to find magnetic field here, firstly, I will drop a symmetrical axis here. Symmetrical axis. Now, if let's suppose radius of this hollow the cylinder is r, and this particular point, if this particular point is small r distance apart, if you want to apply Ampere's circular law here, so you need to create a loop firstly. This is my loop. It's my loop, no? It's my loop, Ampere's loop. Ampere's loop. Now I will write the equation. What is the equation? B, okay, so integral of B dot dl equals to nu naught summation of I, which is enclosed. Okay, I can write here, which is B dl cos theta integration nu naught. Inside current I, only I is there, no? So you can look here. If current is going upside, so here magnetic field is inside, magnetic field is outside. So I can write it like this, like clockwise way. So you can take an element here, a small element dl. So dl will be in the same direction of the B. So theta is also 0 degree here. So I can write B integral of cos 0 is 1. So I can write dl only. Nu naught I. Okay. Now B. What is integral of dl? It will be 2 pi r. Why? Because loop is only circle, no? So B came out to be, it is nu naught I divided by 2 pi r. So outside, it behaves like a wire. Outside, it behaves like a wire. Now, let us talk about the inside point. If we talk about the inside, this one is inside point. Point B. Now make a loop here. Make a loop here. Okay, loop here. So second part is inside. Write equation for inside. It is B dot dl nu naught summation of I enclosed. You can see here inside no current is present, so the whole thing will be 0 now. Why? Because I enclosed is 0, so therefore it just replies us that B inside is 0. So now if we talk about the hollow cylinder, hollow pipe, thin walled pipe, outside magnetic field is present as nu naught I 2 pi r, but inside magnetic field is 0. Why? Because I enclosed is 0. Because I enclosed is 0. Now you can see here, my magnetic field is depending on the distance between the symmetrical line, axial line, and it inversely proportional. Now, if you want to make a graph, between R, between B, this particular point where my R equals to R, that means it is on the surface. So this side represents inside. So inside it is 0. Outside it is inversely proportional to R. It is B is inversely proportional to the R. So this graph represents rectangular hyperbola. It is rectangular hyperbola. Why? Because the power is 1. If the power is 2, 3, 4, so we can write it is hyperbola, not a rectangular hyperbola. Easy? Easy or super easy? Huh? Easy or super easy? You're not responsive, na? So I will assume that it is super easy. Okay. Now, third application part. Okay, now third application part. Third application part is magnetic field. Magnetic field due to solid current carrying long wire. One more name as thick current carrying wire. One more name as straight wire with a radius will be given or diameter. These are some languages which you will find in numerical. These are some languages that you will find in numericals. Either they will ask you a magnetic field due to a current carrying long wire. Long means infinitely long, right? Or you will find the magnetic field due to a thick current carrying wire, thick. Or you will find magnetic field due to straight wire with some radius or diameter. It is also a case of solid wire, solid cylinder thing. Now, solid means the material is present inside. If I try to make it now. Okay. So my solid. Okay. Solid means material is inside. This material is inside filled. It is not hollow inside. Symmetrical axis. Okay. Now, first part, if you are giving current I, the I current will flow throughout the volume. The I current will flow throughout the volume. Now, I will take a point outside. This is point P. If you want to find magnetic field, what you need to do? To apply Ampere's law, I need to make a loop. Okay, this is a loop. I need to make a loop. And this is what? Ampere's loop. So my magnetic field would be out inside, loop like this, and dl is inside. So you will find also the theta is 0 degree. First case, outside. Outside. So my equation is integral of b dot dl equals to nu naught summation of current I that is enclosed. Can I write here b dl cos 0 degree? Then we have nu naught summation of current is I only. Now cos 0 is 1. I will take B outside. So what is dl? Dl means 2 pi r only. If this distance is r, this one is r, I can write 2 pi r. And if the distance or the radius of this cylinder is r, it is 2 pi r nu naught times I, which simply indicates outside my magnetic field came out to be, it is nu naught I divided by 2 pi r, which is inversely proportional to the 1 by r. So you can see here, if we are talking about the wire or hollow cylinder or a solid cylinder, outside, for outside point, these three will behave like a same. These three will behave like a same. One second. Okay. These three will behave like a same. One second. These three will behave like a same. Okay. Now look. Here, if we now, what happens? One second. Now, if we talk about the inside point, this inside one, inside. Okay. It is point, let's go A. Now we want to calculate magnetic field here, so I will just cut a small loop. I will cut a small loop. Done. Now, how to do it? I will write here point number second. Inside. Inside. Look beta. My current I is flowing. I is flowing through this whole area. What is the area? So area is pi r square. That means through 1 unit of area. Through 1 unit of area, my current flow is 1 by pi r square. So now, if this radius is r, let us suppose it is r. So what is the area of this one? It will be pi r square. So can I write now the current which will flow through pi r square? It is equals to I divided by pi r square multiplied by pi r square. Pi cancel out. So I can write I, which is enclosed. I enclosed came out to be I r square by r square. It is enclosed current. This one is the enclosed current. Done. Now we can apply the law now. Which one, sir? Closed integration of b dl cos theta simply equals to nu naught summation of I, which is enclosed. Done. B cos 0, simple cos 0 is 1. Now I can write b dl. What is dl? It will be 2 pi r only. Nu naught. What is current inside? Current inside will be I r square by r square. So can I write now my B inside my magnetic field would be equals to, if it is visible to you, I can write it will be nu naught I r square whole divided by, it is 2 pi r into r square. R cancel out, so which came out to be, it is nu naught I into r whole divided by 2 pi r square. This is my required equation. This one is my required equation. Done. Done now. Now you can see here, if we are outside, it varies inversely. Now you can write B is inversely proportional to 1 by R. This one is outside. If we talk about this inside one, so this inside one, you can see that my magnetic field is proportional to the R. Now, if I need to make a graph, I will make a graph like this. RB. Point here where R equals to R. That means at the surface. Inside, it is directly proportional. This graph means it is inside graph. Directly proportional. Then outside, it is same rectangular hyperbola. It is outside. Clear? Easy or super easy? Easy or super easy? Easy or super easy? Huh? Easy or super easy? Super easy. Now, let us suppose in my numerical, if current is not given, I can write in terms of current density. In terms of current density. Do you know what is current density basically? Yes, sir. So my current density means it is J, which is equals to current per unit area. That means current is equals to JA. JA. You can see now, look, integration of B dot DL equals to nu naught summation of I current, which is enclosed. Look, current density is same, no? If material is same, everything is same, conditions are same, so you can write density is same. So now you can write here it is B dl cos theta integration, then it is nu naught of summation of I enclosed. Done. I can write B. What is dl? It is 2 pi r cos 0 is 1 nu naught summation of current. Look here. Look, this density is same but area changes. Yes, sir. I can write integration of J dot dA. Okay. I can write B into 2 pi r nu naught J is constant integration of dA only. So B it is 2 pi r nu naught J. What is the integration of dA? Sir, that is pi r square. That is pi r square. So I can write here B came out to be nu naught J pi r square divided by it is 2 pi r. Pi cancel out, r cancel out. B came out to be nu naught J, then we are having r by 2. Magnetic field in terms of current density. Magnetic field in terms of current density. Is everything good up to this particular point? Is everything good up to this particular point? If yes, then let us do some numericals. Okay, let us do some numericals. In this class, we will finish solenoid and toroid also. Let us do some numericals then. Okay, this one. Look now. It's my numerical. It's my numerical. Numerical state is that a solid cylindrical wire, which is given to us solid cylindrical wire. It is having radius r and current I is flowing through it. The ratio of magnetic field at a point located r by 2. I guess r by 2 simply indicates inside point. And 2r. 2r means it would be outside point. Outside. Okay. Distance away from the axis of the wire. That means we have to find out B inside to B outside. This thing we need to find out. This thing. Okay. Look now. What is B inside? What is B inside? We discussed it now. It is nu naught I r divided by it is 2 pi r square inside. Nu naught as it is, I current as it is, but it's r. R is r by 2. Whole divided by it is 2 pi r square. Done? Clear now? Equation number first. What is B outside? What is B outside? Is it only nu naught I divided by 2 pi r? Yes, sir. I will write here nu naught I 2 pi. What is r? R is nothing, it is 2r. Second equation. Divide these two. Okay, so can I write now B inside to B outside equals to nu naught I r by 2 whole divided by 2 pi r square whole divided by nu naught I 2 pi 2r. Look now, nu naught cancel out, I cancel out, 2 pi cancel out. Then we have these two cancel out. R into r square, r square, r square cancel out. I guess my answer came out to be 1:1. Which one? Option number A. 1:1 is my answer. Easy or super easy? Easy or super easy? Huh? Super easy, no? Okay. Next numerical. Next numerical. Okay, now you need to take only 10 seconds to just give answer to this one now. We are having thick current carrying cable. Thick current carrying cable means a solid one, thick. It carries a radius r. Current is I, uniformly distributed across its cross section. The variation of magnetic field with respect to the radius or distance. Okay, I guess now we discuss it now. Inside it is directly proportional to rectangular hyperbola. I guess option number 3. We don't need to think about it now. Option number 3 is correct answer. Done. This one now. Give me answer of this one now. This one. Look. A long hollow copper wire. That means it is hollow inside. It carries current I. Then produced magnetic field will be. Wire will be its magnetic field. Sir, both inside outside. Yes, outside is present but inside not. Option is correct. Sorry, wrong. Inside the pipe it is wrong. Why? Because inside is 0. Outside is present. It is wrong. So only option is which one? 2. Outside only present. Nu naught I 2 pi r. Easy numericals, right? Hello, beta. One more numerical. I have plenty of numericals for you. Don't worry about it. Okay, this one now. This one now. Yeah, great. Now, give me answer of this one now. Give me the answer of this one now. I am giving you third question. Give me the answer of this one now. So I will just explain this numerical to you firstly. A current I flows along the length of an infinitely long straight wire. Thin-walled. Thin-walled means inside is hollow. Then, one thing that we know that B inside is 0. B outside is not equal to 0. It is nu naught I 2 pi r. Done. So now I need to check the options now. Look, the magnetic field at all points inside the pipe is same but not 0. It is 0. Incorrect. Last one. The magnetic field is different at different points. No, it is same at 0. The magnetic field is 0 only on the axial position. No. The magnetic field at the point inside the pipe is 0. Yes, option number 2 is correct. Done, beta. Option number 2 is correct. Now one more numerical. Which one? Okay, this one now. This one now. So what we are having? A straight wire of diameter 0.5 mm. So we are having a wire diameter. That means we are discussing with what? Solid cylinder. Current is 1 ampere. Now we replaced this wire with another wire of 1 mm radius or diameter. Current is same. Then strength of the magnetic field is. Do you know what is the equation for magnetic field? Yes, sir. Outside it is nu naught I 2 pi r. Look, nu naught is constant in both the cases. I is constant in both the cases. 2 constant, pi constant. What is r? R means distance of your point where you need to calculate magnetic field from the center of the wire. So here everything is same, only the diameter of the wire increased. So we don't have any parameter in our equation which tells about, yeah, it depends on the diameter, right? So you can write here independent independent on the diameter. You can write same as option number 4 is correct. Option number 4 is correct now. Okay. So we are having one more numerical. Yes, this one now. This numerical. Okay. This numerical is about, you can see here, we are having a long straight wire. Radius is 3 mm. No use. Carries a constant current distributed across uniformly perpendicular. If the, yes, J, current density is given. Magnitude magnetic field, firstly 2 mm from the axis of the wire, 4 mm. That simply indicates if the radius is 3 and you are dealing at 2, so this point indicates it is the inside point. If it is 4, which indicates it is the outside point. Find in both the cases. No issue, sir. Look now. No issue, sir. Look now. So you can see here, what is the formula for inside? It is long straight wire. What is the formula for inside? Huh? Okay. So inside formula. Inside, it is nu naught I times r whole divided by, it is 2 pi r square. Or in terms of current density, it is nu naught j. Nu naught means 4 pi 10 to power minus 7. J is 100, it is 100. R is 2 mm, it is 2 mm, m means 10 to power minus 3 meter, whole divided by 2. 2 cancel out. We are having 4 pi, so I can write it like it is 4 pi 10 to power minus 7 plus 2 minus 3. It is 10 plus 2 minus 8. 4 pi 10 to power minus 8. Okay. 4 pi, 4 pi, 4 pi. This is wrong answer. 10 to power minus 8 minus 4 minus 8. This one is a wrong answer. Now we are having these two options, no? Second and third. Okay. So we are having 4 pi 10 to power minus 8 Tesla. Now inside, sorry, outside. What is outside formula? Nu naught I 2 pi r. Done. Nu naught. What is I? I is j into a. J into a. What is a? A is pi r square. Whole divided by, it is 2 pi r. Pi cancel out. Nu naught is 4 pi 10 to power minus 7. J is 100. R. What is R? R radius means this one. 3 10 to power minus 3. 3 10 to power minus 3. It is square, na? Whole divided by, we are having 2, then R. R is how much? 4 10 to power minus 3. Done? So look now. 4 cancel out. 1 cancel out. I can write it like 3 is 9. It is 9 pi by 2. 10 to the power minus 7 is minus 3 plus 2. It came out to be 9 pi by 2. 10 to the power minus 8. Tesla. Minus 2, 10, 9 pi 2 minus 8. Look, this is now incorrect. This one is correct. Option number 3 is correct. Option number 3 is correct. Okay. Option number 3 is correct now. Done? Easy? Easy or super easy? These are some numericals that I am just finding. These are very good numericals. So now let us start next topic known as solenoid. Solenoid. Okay. What is solenoid? Basically, we are having a non-conducting rod. We are having a non-conducting rod. On this non-conducting rod, we are just placing a wire. This is my wire. And now we are giving current I. Current I will leave. Okay. Current I. So what this thing is? Non-conducting material. And this arrangement is known as solenoid. And you can write it is a type of electromagnet. Type of electromagnet. Okay. Type of electromagnet. Something you need to know now, that is I is current. I is current. Then you will find capital N here, that is number of turners. Number of turners. You will, if the length is L, suppose if the length is L or something like that, you will find small n, that would be N by L. So which indicates number of turners per unit length. Per unit length. Okay. So if you find I is current, capital N means number of turners, small n means number of turners per unit length. Look better, if we are talking about electromagnet, that simply indicates magnetic property gets created due to the flow of electricity. If no electricity is there, no magnetic effect is there, because we are dealing with the chapter na magnetic effect due to electric current. Okay. Look now. If let us suppose, look now, if the radius of this non-conducting material is r, small r, and if let us suppose if length is more than r, if the length is more than r, that means a long solenoid. It is what? A very long solenoid. Okay. So you can write a long solenoid. Solenoid. A long solenoid. Done? Okay. Now, for this long solenoid, just remember magnetic field inside. Inside magnetic field, it is equals to nu naught Ni or nu naught N by L I. These are two formulas that you need to remember for a long solenoid. Okay. Specific case is there. long solenoid only, then the formula is nu naught Ni or nu naught NLI. Sir, what about the outside? If you will get a question, sir, what about the outside? For outside, I will just show you one slide. Look better. This rod is very thin. Okay, this cylindrical thing is very thin. So look here, my current is going inside. Look now, it is going inside current. It is going into the plane. Here it is coming from the plane. So cross represents electric. The current is going inside. Cross represents current is going inside from this side. And dot represents current is coming out from this side. And the rod is very thin. Now, suppose we are talking about this particular point P. Okay, due to this current, my magnetic field will be here. It is B1. Due to this current, if we talk about my right hand, now it will be here, B2. Done? Done? No. You can see now. You will say, sir, this is R1, and this side it is R2. But you can see now the difference between them, that is this one, it is R dash. R dash is very small, very small. It is very small. So you can write here B1 is approximately equals to B2. Therefore, my B net outside is approximately equals to 0. B net approximately equals to 0 outside of my solenoid, long solenoid. Perfect. Now you want to just got about, so wire will be the direction. Wire will be the direction. Look, inside. Let's say we are taking a point here now. It is my inside. Actual point inside here. Okay. So take your hand. It will be inside. Okay. So my net magnetic field will be here. You can take your right hand and you can get the direction. How, sir? Take your right hand. Below it is outside thumb. Okay. B is here. Now upside it is inside. Palm is left side. So it gets what? Add. So B net is left side. So if we're talking about the long solenoid, equation is nu naught N I or nu naught capital N by L into I. Now, second case is if we are having finite rod, finite solenoid. Finite means length is not that big. Okay. For that thing, look now. I will make a diagram. Okay. Then a point P here, just connect these two terminals. If this one is theta1, this one is theta2. Do you know what is the magnetic field at P? Magnetic field at P, it would be nu naught Ni by 2 cos theta 1 plus cos theta 2. Just remember this one. Magnetic field at point P would be nu naught Ni by 2 cos theta 1 plus cos theta 2. Now suppose we are dealing with infinite. If we are dealing with infinite solenoid, I guess infinite solenoid means I need to extend these things. Now look, infinite means here, somewhere here, no? Somewhere here. So this angle is approximately equal to 0. And so that this one, it is 0. For what? Long. You can write theta 1 equals to theta 2 both equals to 0 degree. Now write the thing in equation. So equation means it is nu naught Ni by 2 cos 0 degree plus cos 0 degree. So I can write nu naught Ni by 2 cos 0 is 1 plus cos 0 is 1. It is nu naught Ni by 2, 1 plus 1 is 2, 2 to cancel out. So it came out to be nu naught Ni. Done? So magnetic field due to a long solenoid inside is nu naught Ni, outside is 0. If we are dealing with finite, it is nu naught Ni by 2 cos theta 1 plus cos theta 2. Clear? But it is between, it is not at the extreme ends. But let us suppose we need to discuss. If let's suppose we will take this point. If we will take this point here, P. Now, how to find magnetic field at endpoints? At endpoints. My solenoid, let us suppose length is L, radius is R. We are talking about this particular point. Now, connected these two things. Now, here one angle becomes 90. So, theta 1 is 90 degree. And this angle is approximately 0. Okay, it is 0. So, you can write now nu naught Ni by 2 cos theta 1 plus cos theta 2. It is nu naught Ni by 2 cos theta 1 minus cos 90. And this cos 0 is 1. It is nu naught Ni by 2. It is 0 plus 1. So I can write here it is nu naught Ni by 2. So that simply indicates magnetic field at the end point equals to magnetic field at the center divided by 2. Simple. Simple as it is. Done? Clear now? Now let us suppose we are having a solenoid. Suppose we are having a solenoid like this. Look now. We want to make a graph of it. A graph. Look. Magnetic field inside is, one second, I will write here it is nu naught Ni. At the end it is nu naught Ni by 2. Inside it would be somehow constant. Okay, it will be somehow constant like this. At the end it decreases like this. Then outside it decreases like this. Okay, this particular point means nu naught Ni by 2, same as this one be, and this value is nu naught Ni. A very good graph which represents this particular thing. Done? Okay, let's draw one numerical based on the same topic. Let's draw one numerical. One second. Okay. Okay, this one numerical. Okay. So numerical is 3 identical long solenoids P, Q, and R connected to each other in this figure if the magnetic field at point P is 2 Tesla. So find magnetic field of Q and R. So sir, what is the magnetic field? Which will be B is equals to nu naught times Ni. We are having identical means and same nu naught same. So my magnetic field is proportional to the I. If current I is coming, due to the identical properties, current get is half divided. Half. Okay? Half get divided. Now, if the look now, if current is half, so magnetic field will be half. Here is 2 Tesla, here will be 2 Tesla by 2, here will be 2 Tesla by 2. It is 1 Tesla only and 1 Tesla only. So my answer is how much? 1 Tesla. Easy now? Easy or super easy? Easy or super easy? Easy or super easy? Huh? Okay. So let's talk about one more property, that is thick hollow cylinder. Thick hollow cylinder. That means the thickness is more. Suppose we are having a inner one. Inner one is like this, inner one. This one represents the outer one. And material is available. Okay, here material is available. Here now, look now. If the radius of inner one is given as A and the radius of outer one is B, where is material present? So you can write that, sir, material is present only pi B square minus pi A square. Only material is present in this particular area. So if you need to get the outside magnetic field, outside is integration of B dot dl nu naught summation of I enclosed if current I you are giving. So you can write B. I can write simply B 2 pi r na. I don't need to just do the derivation whole then. Nu naught I, so B came out to be same nu naught I divided by 2 pi r. This one. Okay. But one thing is there now. If you want to find for the inner one, okay, I will write here. If you want for the inner one, inner or inside part, inside. Suppose here, inside means here now. So if the radius here is r. So how to find it now? Look, my current I is present in the area pi b square minus a square. Done. In one unit, my current will be I divided by pi b square minus a square. Now what will be the area enclosed? Now it will be only this one. So this area is equals to pi r square minus pi a square. That means pi r square minus a square. So in this particular value, so my enclosed current will be equals to I pi b square minus a square multiplied by pi r square minus a square, pi cancel out. It will be I r square minus a square divided by b square minus a square. It is enclosed current. Now you can place the values in the equation. What is the equation now? Closed integration of B dot dl equals to nu naught summation of I enclosed. So it came out to be 2 into 2 pi r nu naught I r square minus a square whole divided by b square minus a square. So b came out to be nu naught I divided by it is 2 pi r square minus a square whole divided by b square minus a square. This one. Easy? Easy or super easy? Easy or super easy? Now, okay, let's do one numerical then. One numerical. Mm-hmm. One second, beta. Because I have not taken those numericals. Mm-hmm. No, I have not taken those numericals. So we can do one thing. So let us do a one thing only, right? One question now. Question is like, if length we reduced it to the half and number of turners is also n by 2, then what will be the effect of magnetic field if initially is B? What is nu B dash? So B is equals to nu naught n, that is it is per unit length, then I. So now in second case it would be nu naught n is n by 2, that is it is L by 2 into I, cancel out, so B dash came out to be B. B dash came out to be B. Okay, I think we are done with today's class. Now in tomorrow class we will discuss toride. We will discuss toride and many things with associated with toride. Then we will do a lot of things. Okay, if you have any doubts or anything like that, you can just let me know in the comment box. If not, then you can just go to the Telegram and write your question physics there. I have my Telegram channel. You will get the notes of the class and many great things there also, and mind maps also, right? Thank you for today's class. Thank you, beta. Thank you, thank you, thank you, thank you, thank you, thank you. Mm-hmm. Bye, beta. Bye. Good night. Bye. Good night, beta. Thank you. Bye.